All right, it's me here again. Hopefully you enjoyed the lesson there about 7.2, and I'll try not to talk about angle FLU or arc FU in this video lesson. That was definitely not on purpose. Here, what I'm going to be talking about, if you want to go to your textbook here, I'm going to be talking about actually lesson 7.3 and 7.4 together. We'll be discovering things about tangent lines, and remember that tangent lines are lines that are going to intersect the circle in one spot. So if you come over here and you look at this circle right here, this line right here is a tangent line. Okay, if I was to make a line that intersects, not a segment, okay, but a line, okay, that intersects in two spots, okay, this is what we're going to call a secant line. Okay, so there is going to be a difference here. In today's lesson, we are talking about tangents. And the one thing that we'll discover about a tangent is when it intersects at one spot right there, if I was to measure the angle that it creates with the radius and this tangent, no matter where we put that, okay, point right there, this tangent line as I move it around, okay, should be, and you can see that angle right there, and regardless of where it is, okay, any tangent line is going to be perpendicular to, okay, the radius. Okay, so that right there has just talked about conjecture 66, that tangents to a circle is perpendicular to a radius drawn to the point of tangency. So this point T is called the point of tangency, and anytime you extend a radius out to a tangent line, that angle that we form right there will be 90 degrees or called perpendicular to the radius. With that said, you then can come up here and you can draw in definitions tangent circles. So circles can be drawn externally tangent and circles can be drawn internally tangent. So if these two circles intersect at one spot and are both on outside the circle, these are externally tangent. They don't have to be the same size. Okay, these two appear to be the same size, but I could, okay, come up here and draw this circle right here, obviously bigger than that circle right over there. If I had a wonderful drawing tool, which I don't know if I have, I could draw one here that was obviously a lot bigger than it. Okay, or you could draw two internally tangent circles, which you can see the centers are on the same, are collinear to one another. Okay, but they will be different size in their radius and in their circumferences. Okay, so that led us through conjecture 66. Okay, then coming over here to 67. Okay, if we have two tangent segments, okay, or at least two tangent lines that intersect at a common point. So if I came over here and I was to construct another tangent point, let's say it goes through point G. Okay, so to do that, I could make, and if you wanted to construct one, now that you know that it's perpendicular, you can draw the radius right here, and you could say make a perpendicular line go through G, perpendicular to the radius, construct, okay, a perpendicular line, and that, okay, right there in itself has constructed a tangent line. Now these two tangents are going to intersect at that common point H, and if you were to measure the distance from H to the points of tangency, okay, the one thing that you're going to notice here is this is 9.79. If I measure from H to B, that measurement right there is also 9.79. No matter what the size of the circle is, you can notice these lengths right here remain the same no matter where these tangent lines, okay, intersect at. That distance from the point of tangency to the tangent point, so the point of the intersection to the point of tangencies, those distances will always be the same. So this right here, okay, was conjecture 67 that said the tangent segments to a circle from a point outside the circle are equal in length. Okay, and that's enough right there to go through and learn about the tangent points and all about tangents in the circle. Okay, that's then going to lead us into Okay, a new definition that we're going to have about angles and arcs. Okay, and what we did learn previously about in central angles is that if we had a central angle, that this central angle was the same measure as its arc. And I do have, okay, a central angle right here, and you can see that if I came up here and I measured, okay, this central angle, okay, that measurement, okay, is going to be 149 degrees if I measure its arc. Okay, this arc's measurement, okay, is also 149 degrees. Obviously, if I change the angle's measurement, the central angle's measurement, its arc right here is going to stay that same measurement. I don't ignore this funny way of the C26. I think that says circle 26 on, that's what this one's labeled. So it's arc BD on circle 26. Okay, is 147 degrees. Now the thing that I have here is, what I want to notice here is, if I was to make an angle that is not at the center. Okay, so here I have angle, and I don't like that there's another D here. So let's change this angle right here to, how about K? Okay, so we have angle BKD. Okay, and this angle right here, if I was to measure it, okay, is this angle right here going to be bigger or smaller, okay, than that central angle? Okay, if you had to guess, just look at it right now. Does it look like it's bigger or does it look like it's smaller? Okay, to me, in fact, it does look like it is smaller. If I move this thing closer and closer to the center, you can see if I put it right here on the center, I could get it to be exactly, okay, 147 degrees. But as I move it further and further away, okay, so that I get it closer to, okay, the circumference, you can see the closer I get it to the circumference, the smaller this angle is going to be. Okay, now for the sake of just observing things, I'm going to make this angle right here as accurate as I can, okay, to 140 degrees. So here I have angle and its arc at 140 degrees. So as I move this here closer and closer to the circumference, notice the number that I'm coming close to. I'm coming close to, and I just had it here before my finger slipped here, okay, to 70 degrees. Now there is a correlation here between this 70 degree angle and that 140 degree angle. Okay, and if I want to move this out of here right now, and okay, I'm just going to put this off to the side right here. Actually, I'm going to delete this part right here, and I made this inscribed angle. Now this dark angle right here, angle BAD, is what we call an inscribed angle. We had a central angle goes to the center, an inscribed angle goes to the circumference anywhere. Okay, and if I was to measure this inscribed angle, its measurement, okay, you can see that this measurement, okay, right here, and I can actually come up here and I can use my calculator, okay, and I can calculate this angle right here, multiply it by 2, okay, and notice that anytime that I multiply this angle right here by 2, okay, no matter what I do right here, this angle times 2 is going to give me this arc's measurement. So that arc right there, which is BD's arc, so if I double the inscribed angle, it will give me the arc's measurement. No matter where I put, okay, that angle, no matter what size I make the arc right here will always be twice as big as that angle. Okay, notice these two things. That angle is smaller, and I always remember if I come over here and I was to, okay, measure, okay, this arc right here, okay, this little arc, and we can make, okay, a measure, okay, that arc right here. Well, that's going to measure the other one. Oh, never mind. Okay, so, okay, this angle right here is half of that arc. Okay, so that comes back here, and we now have a rule here for, okay, chapter 7.3 or section, okay, this is 7.4. Whoops, I had it right here. Okay, and that says the measure of an inscribed angle in a circle. This inscribed angle is going to be 1/2 of its intercepted arc's measure. Okay, so the inscribed angle is half of its arc. Now, if I was to come up here and I was to put another inscribed angle, so if I was to make, oh, let's say this angle right here, okay, let me get rid of right now this central angle so we have less in the picture here. And I was to measure angle BE. No, I don't think I have that at the right spot. Okay, measure angle BED. Okay, so if I measure that angle, no matter how many of these inscribed angles that I have, okay, I can do 1, I could do 2, okay, I can measure as many as I want. Okay, notice these inscribed angles, if they intercept the same arc, they intercept this arc right here, BD. Now, the arc that intersects has to be between the angle. It's not on the outside here. It has to be between it. This angle right here is going to be half of its arc. It's also half of this arc. No matter what size or what I put an angle up here, okay, I can put as many of them as I want right up here. So I'll put this one right here. We'll display this one with a different color. Okay, so this one, okay, right here, okay, this red angle right here, this blue angle right here, and this black angle right here, no matter what I do, okay, all these angles are going to intercept the same arc. Well, they would have intercepted the same arc, okay, if I had it at the right spot. Okay, this one might be a little bit off here because I didn't click on the right spot here, but you can see here, yep, it's still good. Okay, they're all going to be 34.3, which is half of this amount. That's a rounded amount right here. That's why it's not quite exact. But you can see as I double it, I do get that arc's measurement right there. So that right there has talked about, okay, conjecture number 69. Inscribed angles that intercept the same arc are the same measure. So in this angle right here, angle QAP is going to have the same measurement as PBQ. Okay? All right. This next one's kind of an obvious one here, but if I was to come over here, okay, and make a semicircle here. So if I had a inscribed angle, and if I was to measure this angle right here, okay, and I measure its angle, it is 107 degrees. I know that if I was to inscribe it into a semicircle, okay, notice, well, the semicircle BCD, that's going to be, okay, 180 degrees. Notice the inscribed angle is a 90-degree angle. No matter how many of these inscribed angles that I put, okay, into this shape, if I measure, okay, this blue inscribed angle right here, BCD, measure that angle right there, it's also going to be 90 degrees. So their arcs for semicircles, okay, right here, are going to be 180 degrees. You can see that arc right there is 180 degrees. Okay, apparently there's two B's in this thing, so ignore that arc measurement right there. But if you double that, no matter how many, I could put a third, I could put a fourth, okay, no matter how many of these inscribed angles I put into a semicircle, they're all going to maintain, as you can see as I move them around, they'll maintain at 90 degrees. Okay, so what that's saying here on this one, okay, is if I construct a large circle and construct the diameter, that inscribed angles in a semicircle are going to be 90 degrees. Okay, now my last two right here are going to talk about an inscribed quadrilateral and then parallel lines. These two are probably the more important ones that you have for this section. These are the ones that are more likely overlooked. So do pay attention carefully as I talk about an inscribed quadrilateral. So you can see right here that I have this quadrilateral right here, that it is inscribed. Okay, obviously I can measure its inscribed angles. Okay, so if I measure its inscribed angle right here, so if I have that angle right there, that's 80 degrees. Its arc, ADC, is obviously going to be double that. That's not exactly what I'm going to be referring to here, but if you do measure the angles in an inscribed quadrilateral, so I can come over here and measure all the inscribed angles in a quadrilateral, I know that a quadrilateral's angles have to equal 360 degrees. Okay, that is one thing that you obviously can go about doing. But if you look closer at this thing, there's one more thing that you can talk about here. And it's not just about, okay, all the angles. If you add the 60 plus the 80 plus the 120 or 119 plus the 100, you will get 100 and you'll get 360 degrees. But more specifically, okay, and you can see me add those things. I can come up here, use my calculator here quick. Okay, and you can see that if I add that plus this angle plus this angle plus this angle right here, this isn't obvious. They are all going to equal 360 degrees, no matter what type of, okay, quadrilateral that's up here. You can see no matter what, those angles right here will add up to 360 degrees. Okay, but what I want you to look at is what happens to opposite angles in an inscribed quadrilateral. Okay, there's something that's going to be true about those two and those two angles. And this always happens if the quadrilateral is inscribed in a circle. Not in every quadrilateral are opposite angles have a relationship to one another. But if they're in a circle, and I was to add these things up in a circle, so if I take this calculator and I was to take this angle right here and I add it on to the angle that's opposite of right there, notice it's going to equal 180 degrees no matter where how much I move it to. I can change the size of this quadrilateral. I can change the size of the angles. These angles right here have changed, but you notice they stay at 180 degrees. Not only these two opposite angles, but these two opposite angles, if I was to measure, okay, those as well. So if I clicked on this angle right here, okay, and, okay, add it to this angle right here, you can see these angles right here are also 180 degrees. So opposite angles in an inscribed quadrilateral will always be supplementary. It doesn't matter what size the quadrilateral is. It doesn't matter the size of the circle. It doesn't matter where the points are in the circle. Just now, if it is concave, okay, meaning this right here doesn't actually make a quadrilateral, okay, you can see that this right here is not going to add up to 180 degrees. So you can see those numbers right here changing, but when it's inside of a circle, okay, and does make a quadrilateral, these numbers do stay at 180 degrees. So as you see, okay, right here in conjecture number 60 or 71, the opposite angles in a quadrilateral inscribed in this circle are supplementary to one another. Okay, the quadrilateral right here is going to be called, if it's inscribed in a quadrilateral, this is called a cyclic quadrilateral. Okay, so that is an important one. So do make note of conjecture 71, and eventually we're going to get here number 72 when we make parallel lines. And this is the last one that I'll be doing for this video lesson. Okay, and this has everything to do about parallel lines. So you will see me, okay, on this next one right here, make a line that is going to be parallel to AB. Okay, so I'm going to make a line parallel to AB that's going to go through point D. And I'm going to construct this parallel line. Okay, it doesn't have to, as you can see, this parallel line can go anywhere on this circle. Okay, but the one thing that I'm going to have is I can come over here and let me change, okay, this point right here, because I don't want two, okay, point A's. Okay, I don't know exactly how I came up with 2 point A's. Okay, but okay, if you see me come over here and oh, let's change this one right here so that it is point E. Okay, so, okay, if I was to come over here and move this line right here, you can see that line DA is going to be parallel to EB. Now, maybe this is obvious, maybe it's not, but if I was to measure this arc, ED, okay, measure that arc, so I need to measure its arc right here, which is 32 degrees. If I measure arc EB's arc, you can see it's, well, 69.48. If I measure arc BA's arc, it's 39.89. And then if I measure this arc right out here, arc A, C, D, this obviously major arc, okay, you're going to see that its arc is 224 degrees. Now, as I move this around, I can move this parallel line anywhere about this circle. And the one thing that you'll see is these arcs right here don't have any correlation to one another, but obviously the arcs that are intercepted by the parallel lines, those two arcs are going to have the same measure no matter where they're going to be at. Okay, but the arcs above and below the parallel lines, there is no correlation between these two. Okay, no matter where you put the parallel lines, okay, this is 81, that's 81. No matter which direction these parallel lines go, these arcs that are between the parallel lines, so ED, okay, this arc ED and BA are going to be the same measurement. Now, the one thing you're going to have to watch out for is if I make these lines right here so that they're a little bit closer. Okay, now I have a little bit of problem because of where I put C, so let me put C down here so it measures it a little bit better here. Okay, but if I put this line right here equal distance from M as it is from AD, notice I could probably get these two here pretty close to the same if I really tried to do that. Okay, now that's not my point to get these two the same, but what I wanted to make you understand is no matter what you do, the arcs between the parallel lines will be the same. Okay, no matter where it's at. These two right here will not. Okay, so the last conjecture, okay, that we have right here, and this is my last one for today, and the rest of them I will show you here in a bit that are posted on my website, are not in the textbook, but this one right here is my last one that I'll cover that's in the textbook here, which is conjecture 72, that parallel lines intercept congruent arcs on a circle. Okay, so here you now have conjecture 72, okay, through, okay, I guess if you go clear back here to the beginning, which is 61, we have 11 conjectures you can put in there about circles. So this will do the last thing that we'll do here in the textbook. But going on forward from here on out, what you're going to see here in my next one, which is the Johnson conjecture, I named this one for myself, okay, just because it wasn't in the book, I had to give it some name. Mr. Neff used to call it Quacktemeyer. I just like to, name it after myself. Okay, so, but this one here is going to deal with these rules right here about when I went from an inscribed angle to, okay, a central angle. Let me see here. I want to go to, okay, well, this next one that I'm going to have, let's just make this look a little cleaner right here. Oh, actually, let's go back down to this one here. If I was just to look at one inscribed angle right here, and what this one here is that what I talked about here before, okay, was if I had an inscribed angle, and let's say this was, we'll do a nice number, 120 degree arc. Okay, so I have a 120 degree arc. If I was to make a central angle, okay, we know that this central angle right here is also going to be 120 degrees. Okay, but as I move this, as you saw me move, okay, this central angle out further. Let me make this a different color right here. Okay, so we'll come over here and, how about orange? Okay, make this angle right here, okay, move out here. We saw this get smaller and smaller and smaller, and what I'm going to do here is this is going to end up getting out here, and you can see as it gets beyond the inside of this circle right here, okay, it's going to end up getting even smaller yet. As you can see, it's even smaller yet than the inscribed angle, and that's my next Johnson conjecture here. Is it's going to talk about this, what we call a secant angle, because if I made a line right here, okay, this line right here would be made by what we call a secant, because it intersects at two spots, one right here and one right there. So that's why I'm going to call this a secant angle. And that's what's you're going to discover here about the Johnson conjecture number 1. Okay, but for right now, okay, the one thing that you can do, okay, is you can go on to my, obviously, okay, Canvas page, and you can look at all my video lessons that I have posted right here. You don't see video lesson 7.3 and 7.4 here. It'll be right here before conjecture 1. But you can watch conjecture 1, 2, 3, and 4, okay, as well as the rest of these things. Okay, if I go back into, okay, my calendar, okay, from the calendar you get circles. Okay, you should be able to, I will have these posted here, and this will change. Okay, you can do my quizzes. Okay, here's 56, 0568, 51, 6251. Okay, then once you're done with those quizzes, obviously you may want to do some of the worksheets, okay, that were here before you do those. That's completely up to you. The only thing I'll be able to see that you did do, and my goal for you is to have these two done, okay, by tomorrow, I would hope, and then go on to by Wednesday, okay, watch conjecture number 1. These are short lessons. You should easily be able to watch these things, okay, within, I would say 15 minutes. And then just do the quizzes. You can do them as many times as you want until you kind of understand the information. This not only allows you to retry and relearn, it also allows me to track to see that, and again, my goal is by tomorrow to have 75% of you have at least taken this quiz right here, and 50% of you have taken these two quizzes. At least 50% of you taken this first one. Okay, I'm hoping at least 40% of you at least take this one. And then by Wednesday, I'm hoping that all of us have at least done this one right here. So 100% of us have done by Wednesday this one, and okay, 75% of us have gone through this by Wednesday. Okay, that'll lead us, okay, into the application worksheets. And if you don't want to do the application worksheets, that's fine. Go into continue to do some more quizzes that I'll have posted here about my Johnson conjectures. And I have one of my quizzes right here that's going to go with the inside and the outside. You'll have to watch both of these video lessons first in order to do this quizzes, okay, right here about video lesson number 2 and, okay, conjecture 1 and 2. Well, that's going to conclude my lesson for today. Hopefully you have learned enough information from the information I have. This one was a little longer, a 30-minute lesson, but again, hopefully it keeps you entertained, or at least fresh on your geometry skills. You have a good day, and again, email me, text me, whatever you have, to let me know if you have any questions, and even more, I'm getting bored here at home too, so I do like hearing from you. So feel free to tell me about your day, or at least any questions that you have about math. Have a good day. Johnson out.